A wire with radius A carries a current I. The current is uniformly distributed throughout the wire. In part A, we are to use Ampere's law to calculate the magnetic field outside the wire, and in part B, we are to calculate the magnetic field inside the wire. Ampere's law is very similar to Gauss' law in its structure. In both cases, we define a closed integral over some sort of imaginary geometrical form. In the case of Ampere's law, we are using a length. This is what distinguishes it from Gauss' law, where we used a closed area. The other difference is that although Gauss' law talked about the charge enclosed by a closed surface, Ampere's law talks about the current that crosses through the area whose perimeter is defined by our Ampere's path. Let's begin with region 1, which is outside of the infinitely long wire. Our intent is to find the magnetic field at some point which is located a distance r from the middle of the wire itself. As we remember, magnetic fields form circles around current elements, and so the magnetic field expected at the point of interest should also form a circle. Ampere's law itself becomes maximally simple if we simply follow for our Ampere's path the direction of the field, meaning that our path will be a circle. Two quantities are necessary to define to continue. The first would be the length, and the length of the path is the circumference of the circle, which is 2 pi times its radius. Also, we need to find the current that is inside this path, and because the path is in region 1, all of the current, or an amount I, passes through. Plugging in both of these quantities, we can solve for the magnetic field in region 1 as mu0I divided by 2 pi r. And this ends our analysis of region 1. Region 2 is slightly trickier because the point at which we hope to calculate the magnetic field is going to be located inside the wire. For this reason, the radius r that leads out to the point is smaller than the radius of the wire itself, which is a. Nonetheless, our technique is the same as before. We recognize that the magnetic field will make a circular path, and so Ampere's law simplifies to field times length is mu0 times current in. Just as in the previous problem, the length is the circumference of the circle, so it is 2 pi r. However, this time, the current enclosed by the Ampere's path is not the entire current, but only some fraction of it. To deduce the appropriate fraction, we recognize that the Ampere's path essentially acts like a cookie cutter applied to a sheet of cookie dough. The piece that we have selected represents some fraction of the total area. For this reason, we multiply the total current by the area we have taken, pi r squared, and divide it by the entire area available across the wire, and that is pi a squared. Conveniently, the pi will cancel out, and so we're able to solve for the magnetic field itself, mu0I r over 2 pi a squared. Finally, no magnetic field or Ampere's law calculation is complete unless we have included a sketch of what the magnetic field looks like. A proper sketch will have the magnetic field itself along the vertical axis, and this is plotted as a function of radius. Each axis should have some tick mark. The boundary from inside to out is located at r equals a, and that will be the tick mark on our horizontal axis. And what we recognize is that the green formula is the one that applies for r less than a. This formula contains a series of constants, and the variable r in the numerator, therefore it is represented by a straight line. In the region beyond r equals a, we will use the red formula, and this has a series of constants divided by r, and therefore follows a 1 over r curve that approaches the axis as so. To make our diagram fully complete, we need one more item, and that is we need some tick mark to label the magnetic field axis. This tick mark will be located at the apex of the distribution, and this is the result we get by plugging r equals a into either the blue or green formula yielding the result mu0I over 2 pi a. And with that sketch, we have completed our Ampere's law derivation.